We're going to do some work in Excel today, covering exactly what Pearsons correlation coefficient is and also what it's not. You're going to understand the math notation behind it, whether or not you barely passed math at school. And in addition, this is going to be a great precursor to the up-and-coming course material coming out, and also platform upgrades for statistical arbitrage at Crypto Wizards. Correlation can tell us whether two assets, for example here, Bitcoin and Ethereum, tend to move alike. Let's say I have the returns of Bitcoin here trending upwards and downwards at times, and Ethereum typically showing the same kind of pattern. So when Bitcoin is going up, Ethereum's going up. When Bitcoin's going down, Ethereum's going down. We would say that Bitcoin and Ethereum here are positively correlated. We could also show the opposite. Let's say that typically if Bitcoin is going up, Ethereum is going down, and when Bitcoin is going down, Ethereum is typically going up. We would say that these two assets now have a negative correlation. Or perhaps Bitcoin is doing its thing and Ethereum is doing something entirely different, in which case there would be no correlation. Correlation can move between -1 and +1, which is really handy because it means we can compare it across different assets, unlike what you're going to learn about with covariance, which is unbounded. When calculating correlation, we typically use the returns, not the price data. And the reason for that is because the price data has memory drift trends baked into it, and the returns give us a like-for-like scenario that we can compare against with our two assets, in this case, Bitcoin and Ethereum. So to understand how the calculation is actually done, first let's just look at a table of returns. We'll call Bitcoin X and Ethereum Y, and this is at each time step, which we'll just call T. T equals 1, T equals 2, T equals 3 for each day or hour or whatever period you're looking at. Let's try to understand, first of all, how to calculate the average of any one of these columns, let's say X or Bitcoin in this case. And you'll know the average is just summing up the column and dividing it by how many items there are. But let's just understand very quickly how to write that mathematically. You see, to sum, we use this sigma notation. And if you're from a programming background, then you will know that this is a lot like a for loop when I explain it to you. So sigma means to iterate over something. And here we're going to iterate over x at time t. So we're going to start with time t equals 1, then t equals 2, then t equals 3. And this sigma sign means to add to itself. So it's going to iterate over this column of x in this case. And it's going to take x at whatever time t and add it in the next iteration. So it's going to start with 0.1 and add that to 0, because that's the first item. Then it's going to go to t equals 2 and add 1.2 to 0.1, which would give us 1.3. And then add 1.3 to 0.8, giving us 2.1, and so on and so forth. So that is the math notation for sum. Now, to know to start at the beginning, we can just put the notation here, t equals 1, underneath the sigma sign or next to it underneath. And above here, we can tell it how many items to go through. So let's say we have 360 rows of data. We could put the number 360 on top here. Now, instead of doing that, we could also just come up with a letter that represents the total number of data points we have, in which case we'll just call this big T. So if we have 360 data points here, we'll just call that big T is equal to 360. Now you know what sigma notation is. The mean is simply just going to be the sum of that column, which we have written out here, divided by T, so how many items there are. Another way of writing that could simply be 1 over t multiplied by the sum, because 1 times this sum area over here essentially is the same thing as this sum sigma notation. Now, the mean or average is also known as the first central moment, but there are other moments that we need to understand. The second is going to be the variance. So we now know what the average is, but typically how much does this asset, X in this case, tend to deviate from its average? To calculate that, let's just say we could take the value at time t at any given point and subtract from it its mean, its average, or what we're trying to simulate here as its expected value. So how much does it deviate from that? Of course, we're summing them up because we're using sigma notation. Now, the problem is we're going to have some positives and negatives, and the negatives might cancel the positives out. So if we actually square this, we're guaranteed to get a positive number. And similar to calculating the average, we can just divide this by how many there are. And funnily enough, actually, we have to do it by how many there are minus 1, because we are using the mean in this, which is essentially subtracting a degree of freedom. I'm not going to get into that. It's a statistics thing. We just subtract 1. If you have data points more than, say, 100 data points, it's really not going to make much of a difference. The symbol that we use for mean is x bar. And the symbol that we use for variance is s squared. That's if we're talking about the sample. If we're talking about this theoretically or in general, referring to the total population of data that might be in existence, then we use this sigma notation here. So sigma squared, little sigma. Great. So now that you understand what the variance is, which is basically how much an asset moves against itself, what about the standard deviation? Well, the standard deviation is just a clever way to scale this number back down, because we squared the variance earlier, or we squared at least xt minus x bar, so whatever the data was at that time minus its mean. But now let's actually remove that squared number, and we can do that by just square rooting. So the square root of this s squared is the standard deviation, which we call s. Okay, now that we understand what the variance is, how to calculate something in terms of how it moves against its own average, what about the covariance? Because if we can do it for one asset, we can do it comparing two assets together. Now, the way that we do that is, again, we use our sigma notation, and we look at x minus x bar, but instead of leaving it there, we now bring y into the equation, which in this case will be Ethereum, and we take y at time t minus y bar. And we don't need to square these two numbers now, because we're dealing with two separate assets over here, and we want to know how they move together, both positively and negatively. We can just leave these multiplied together. And in fact, that's one of the advantages of this calculation. If it's negative, it means that these assets tend to move inversely to one another. So for example, let's say Bitcoin's going up and Ethereum is typically going down. That would be an inverse relationship. So it would come up with a negative number. If Bitcoin's going, say, up and Ethereum's going up, it would be positive. And if they're sort of indifferent, there would be 0. There'd be no correlation. The problem with this calculation, though, is that it's unrelatable. I can't relate this to other assets because the number is really going to be meaningful only to this pair of assets. So we need a trick. We need a way of seeing how two assets move together with covariance, but scaled so that it scales between, say, you guessed it, -1 and +1. And this is where the correlation trick comes in. Because what we can do here is just divide this covariance of x and y, which is essentially what we've got here. We've got this covariance of x and y. We can divide that by the standard deviation of x multiplied by the standard deviation of y. And believe it or not, that will give us our answer. Now, this big, long, complicated thing can actually be shortened. So we can just say that the correlation, which we use the symbol rho for, of x and y is equal to its covariance, as we know, divided by s of x and s of y. And these little subscripts here don't mean to times x by s. It just says that it's the standard deviation related to x, and the s of y is the standard deviation related to y. Now, more commonly, you're going to see this as sigma x and sigma y. Right, let's get on with now calculating this. So the first thing is, I want to work with returns, not price data, as mentioned earlier. So to calculate the simple returns, I'm just going to say, take the current price divided by the previous price and -1. It's the same thing as saying take the difference and divide it by the one before, percentage change. Now, usually in financial time series, you'll see it's very common to use log returns. To do that, we'll just say ln equals ln n, and then this item divided by that item. That will give you the log returns. But we're not going to work with log returns here. We're just going to keep things really simple. And I'm going to use this divided by this -1. And let's drop that down. And this here is going to be BTC, or let's just call it X ret for X returns. And now let's do the same thing for Ethereum over here as well. So here I'm going to copy all of that so we have the same formatting. And I'm going to call this y returns. Let's calculate the average of each of these columns. So here I'm going to call this x bar for the average of x and y bar for the average of y. And here we're just going to use the Excel formula equals average. Or in fact, if we want to do it exactly as the math formulas, which will be useful, let's do it properly. So here I'm going to put in t. T is going to be equal to the count of how many items there are, right? So I've got all of these items over here. That gives me T1826. And then the average is just going to be the sum of this column here, which was our sigma notation, divided by T. And there you go. So that gives me 0.0018. In fact, let's just keep the formatting here the same, 0.002. And let's do the same for y. I'm just going to copy this down and drag this over to refer to Ethereum. So there we are. Let's pop this out to one more decimal place so you can see that these are different numbers. And yes, they are. So here's our first central moment. We have here our averages for each column. But now let's calculate the variance. So let's put in here x var and y var. And so the average is going to be x at any one of these time steps minus its mean squared. So that was the calculation for variance. You can actually see here's the variance calculation here. And it's square rooted because that gets us back to the standard deviation as we saw before. But we need to calculate this variance part here first. We've done x bar and we've done y bar, but now we need the variance for each of these. So the variance is simply going to be this. We're going to say x ret minus x bar, and here that's going to be squared. So to show that that's squared, I'm just going to put this caret sign 2 over there like follows. Let's broaden this out a bit here. And so here we're going to say we're going to take x ret, so the return of x minus its mean, and then we're going to square that. And we're going to drop that calculation down. Let's pop that open to one decimal place. So again, let's keep the formatting the same here. And there we go. Now we need to sum that column. So if we sum that column like such, and then we divide that by how many there are, and this time subtract 1 because we're removing that degree of freedom. And there we are. We've now got our number. And again, let's keep the formatting the same. Now let's copy this column here and insert it there. And here we're going to use the y ret minus y bar. And so that's now looking at y, and we need to subtract here y from that on each of those. So you can see here, for example, this one, subtract the average squared, and then summing all of those up and dividing it by how many there are essentially, that gives us the variance for y. But now what about the standard deviation? So here I'm going to call this x, or let's just call it s of x and s of y. This is the standard deviation. So here, what I can do is I can just take the square root of that number, which is essentially what the square root is doing, right? It's square rooting the variance to get the standard deviation. And the same thing for y over here as well. Let's copy the formatting. And there we go. That's our standard deviation. Now, just to prove that these numbers are accurate, here I'm going to just create an Excel version here. So the average of x is going to be the average of this column here. And the average of y is going to be the average of this column here. The standard deviation, and I'm working with a sample of data, so it's standard deviation.s, is, and what that'll do, by the way, is that'll make sure that it subtracts 1 from t. That's what that .s is going to do, is going to be the standard deviation here of s, like such. And here you can see it's the same number. Let's just keep that formatting the same. So you can see that those numbers are alike. And I'll format this in advance as well. And then the standard deviation of y is going to be this column over here, 0.0437. Perfect. To get the variance, all I need to do is square this number. And that gets me back to that as well. So there we go. We can see that this is in fact the correct calculation. It's following the Excel formula exactly. But we're not done yet because we haven't even calculated the covariance. So let's say covar of, or covariance like this, of x comma y. How do we do that? Well, that is simply going to be this multiplied by this. So covar of x and y, and that there is going to be equal to x, this column over here, minus x bar multiplied by y minus y bar over here. That there is going to be essentially our covariance that we use for correlation. So let's go ahead and drop that down. And so the covariance here is just going to be the sum of all of those divided by, you guessed it, t minus 1. And there you go. Let's format that again here. In fact, let's format all of these. And that is my covariance for Ethereum and Bitcoin. Now, if I pop these open, you can see that these numbers are in fact different. They're not exactly the same number, although to 4 decimal places they essentially are. But now what about the correlation? So the correlation of x comma y, which we could also call rho, is going to be equal to that covariance divided by the standard deviation multiplied by the standard deviation of y. So standard deviation of x, multiplied by the standard deviation of y. And that then tells us that we have a correlation of 0.8057. And just to prove to you that it's the same thing in Excel, I can go equals correl for correlation. And here I'm going to take x and also y. So y, and highlight those 2 columns. And there you go. It's exactly the same number. So you can see now how we got to calculate the correlation using Excel that matches Excel's own calculation or formula exactly. And here is the Pearsons correlation coefficient from scratch. So let's just take a step back for a minute. The first thing we did is work out how much one asset moves against itself. And to work out how 2 assets move against each other, we just took that same idea of subtracting the one asset from its average and multiplied that calculation together for those 2 assets. So x minus x bar for Bitcoin multiplied by y minus, or y of t minus y bar for Ethereum. So that tells us how they move together. And then to scale it between -1 and +1, we essentially just divided it by their standard deviations multiplied together. And so here you can see that Bitcoin and Ethereum are very positively correlated. In fact, you know that already just from looking at this chart. You can see that when Bitcoin's going up, Ethereum's typically going up. When it's going down, Ethereum's typically going down. And so they are positively correlated. If Ethereum was doing the opposite to Bitcoin, we'd say they were negatively correlated or inversely correlated. And that would show something like -0.8 or -0. Whatever. If there was no correlation, that number would be nearer 0. So if this was a +1, it would mean they perfectly correlated. They move identically. If it was -1, it would mean that they move perfectly in the opposite to one another. And if the number was 0 or near 0, it would mean that they move pretty much very differently to one another. So the next question is this calculation actually reliable? Well, we're actually using about 1,800 rows of data here, and that's about 5 years worth of daily data. And it's telling us that these 2 assets are very much positively correlated. And in fact, again, we could see that here from the chart. They're very positively correlated. But how accurate is this 0.8? Well, the problem with Pearsons correlation coefficient, and it is a big problem and it's often overlooked, is that it really assumes that the returns are jointly normally distributed. So that, in other words, another way of putting that is that these 2 sets of returns for X and Y, or Bitcoin and Ethereum, follow a bivariate normal Gaussian distribution if you were to plot the probability of these returns on a bell curve. And another way of saying that is that they follow an elliptical distribution. And the reason for that is if you look at a 3D bivariate distribution and you slice through it, it would look like an ellipse on a chart, right? So you have this elliptical distribution assumption, which we know returns and financial returns certainly don't really follow that. So is Pearsons correlation coefficient a good metric to use? I would say it's a good metric in terms of it's probably directionally correct, but there are other methods which we'll get into with concordance that can really tell you whether or not 2 assets move together. And those methods, which are Kendalls Tau and Spearman's rho, do not assume that these assets follow this bivariate normal Gaussian distribution. Now, if I just go ahead and just highlight that this correlation coefficient is basically over 5 years of data, it's giving us one number, it would be much more useful to know, what is the correlation coefficient right now? What is it over here? What was it over there? How does the dependency and the correlation change over time for these two assets, rather than just one long-term number? But regardless, I hope that this video has helped give you a good introduction into some math notation and also into understanding how to work with Excel. I've found working with Excel and being a programmer very, very helpful. It helps me find and detect errors in my Excel models, and Excel helps me find and detect errors in my programs and make sure that things are running very well. Not only that, anyone can use Excel. Anyone can learn how to type in formulas and follow along and grab this workbook. I'll put a link in the description as well. Very, very easily. I hope this was useful for you. Until the next one, take care and talk soon.